Hey guys, this is Yeser. How's everything going? In this video, I'm going to take a look at 1466, reorder routes to make all paths lead to city 0. The title is very long. There are n cities, numbered from 0 to n-1, and n-1 roads such that there is only one way to travel between two different cities. This network forms a tree. So yeah, there's a tree, then there's no circles. Last year, the Ministry of the Transport decided to orient the roads in one direction because they are too narrow. So one direction. Roads are represented by connections, where connections I equals A to B, like this, means there's a city from 0 to 1. Cool, there's city arrows. This year, there will be a big event in the capital, which is city 0, and many people want to travel to this city. My task consists of reorienting some roads such that each city can visit the city 0. Return the minimum number of edges changed. It's guaranteed that each city can reach the city 0 after reorder. So the black arrows are the original path. From the path, we can see that people in city 2 can only move to city 3, right? And city 3, people in city 3 couldn't move anywhere, right? There's no road outbound. All the roads are inbound. If take a graph like this, we start from city 0, we could see that city 4, the arrow doesn't need to change, it's inbound. So city 4 could reach to city 0, but 0 moved to 1, so 1, the roads from 0 to 1 must be turned away, so turned around, right? This is a red one. And also 3 must be turned around because this arrow is outbound. So it reminds us that we could actually travel through the tree and from 0 and to check the connected nodes. If the arrow is inbound, then it's okay, free to go. If it's outbound, then we mark +1, right? We need to reverse this the arrow, and then we need to handle 1 of 4 recursively. Like for 4 now, it doesn't need to change, so it's okay. For 1, we turn around the road, so it's now reachable to it's now 0 city reachable. So now we take it at 3. The arrow is outbound, so +1. Now we take a look at 2. It's inbound, so it's okay. Yeah, I think we can do something like this. Let's take a look at example 2. For this 0, 1, 2, 3, I think we're saying we step on 0, take a look at 1. The arrow is inbound. Okay, now we take a 2. The arrow is outbound, and then take 3. The arrow is inbound, outbound. So actually, we only need to count the arrows, whether they are inbound or outbound, right? Yeah. So the idea is simple. Now, how we can represent this tree? Well, I suppose we use a map city to other cities, right? City. So how can we check the directions? Well, I could use 2 maps, right? The one is outbound, like this. This is the basic case. We're getting 0, 1, 1, 3, so we get the arrows here, right? We need to get the outbound. Yeah. We could use 2 maps, okay? You use 2 maps. 2 maps. And then we could do like for city 0. For city 0, we just for city 0, we first take a look at the outbound map and then inbound map, right? Cool. Let's do it. Inbound map, new map. That's the outbound map, new map. Cool. Now for each connections. For each connection, this from and to. For from, these are outbound, right? So if outbound map has from, get from, add to. It doesn't have it, we set from, new set to. Well, on the other hand, for the target, it's like 0 here, there will be oh, wait a minute, outbound. Yeah, this is outbound for 0, but now for 1 there's an inbound, right, from 0. So if inbound map has to get to add from. If not, we set it to new set from. Okay, so basically we are keeping actually the arrow here and the reversed arrows, right? And but we are using different maps. Cool. So now we start traversing. Well, we could use DFS or BFS or anything here, or just to make it simple. Let's use recursion. Yeah, let's first use recursion. Okay, we walk. What do we get? We get the city, right? Yeah. When we walk, we need to mark whether the city is reachable or not, right? So, like we say, it's there will be no circles. There will be no circles. For there will be no circles, but when we are we are handling city 0, you first take a look at the outbound map, and then okay, take a look at the inbound map, and 4. Now there's no need to collect, so we traverse 4 again. But 4 now for the inbound will point to 0. So I think we still need to keep track of which node, whether the node is traversed or not, right? So traversed, we keep nodes, cities, new set. When we walk on city, yeah, we suppose that all this when we are walking the city is not traversed, because if it is already traversed, we won't traverse it again, right? Okay, so I think we don't need to check the walk, check the traverse or not for city, but at last we need to add set it to traversed add city. First, we take look at the inbound, which means for city here, we take a look at 4, right? Yeah, if which is inbound, if inbound map has city, then we don't need to reverse the road. We now walk on city. We walk on the all the cities, which leads to 0, right? So for that city of inbound map, get city, we will walk on them again. We will walk on them. Yeah. And 2, we look at the outbound map. If outbound has city, which means for 0 here, there will be 1. Well, that's the case. We need to reverse the road. We keep track of the result. Initialized with 0. If you have one like this, now what it is? It means we need to result a +1, right? And then we go to the next city. Oh no, it's not here. We should put the +1 in the for loop, right? We +1 and work on that again. Cool. Well, you see there's a mistake here. We set the traversed, so when we walk on it, we need to first check if it is traversed or not, right? If is already traversed. If it hasn't been traversed, then we work on it. So here it's the same. If it is not traversed, we +1. Cool. So now, at last, we will start working on 0, right? The origin city, and then we return the result, right? Let's see if it works before we submit. Okay, suppose the case like this, we will step on 0 first, and there is a inbound map, right? Of course, there's outbound map, point 1, but there's no outbound for 0. So you see, there's an inbound. There's here. This inbound map has 0. So for city in inbound get city, which is 1, it is not traversed yet. We work on 1. Not for 1. There are first there are 2 outbound, and then 2. Wait a minute. There are for this one is outbound. 0 to 0.1 is in. Wait a minute. Wait a minute. They're inbound. For here there's this one is inbound, so this is outbound. This is for this arrow for 1, it's outbound. The inbound is for 2. So okay, for 1 there's 0, 2, but 0 is already traversed. And now we go to 2, which is outbound here. So we +1, and then we'll step on 2. 0 is already traversed, and then we go to 2. Again, for 2, 2 has 2 inbound, right? 2 inbound. So we'll go to here, but 1 is already traversed. We take a look at 3, and work on 3. 3 has 2 outbound, and 2 is already traversed. We move to 4, and the +1, so 2. I think this should work, actually. There is a problem. Number 1 is not iterable. What is that? There's a syntax error. I'm sorry. It should be something like this. Cannot access city before initialization. What? Let city of inbound map get city. Cannot access city before initialized. Work on city, add city, if has city. Cannot access city before initialization. City is the parameter, right? 36. Let city. I'm sorry. These actually like from, okay? From. No. Like this is a city. Inbound. So this, if it is inbound, then this is a from actually. If the outbound has city, then this is 1 is 2, right? This is a naming problem here. My bad. Get is a functional, return is value. Inbound map is not a function. Inbound map, which is 35. Get from inbound, get city. We actually create a set. So when we get a city, then you should return a set for let of. It should be no problem. Inbound get is not a function. Wait a minute. Inbound map. New map. Outbound. New map. Let 2 of inbound. This is set, right? What? Ah, I'm sorry. This inbound is inbound. This outbound. This should be outbound. Set. Ooh, cool. I think we're good. Before we submit, allow me to try. Oh, this one, right? Let's try another input, which is 2. Hmm? 5. Yeah. Cool. I think we are okay. Submit. Oh, yeah, we're accepted. And let's try to analyze our time and space complexity. Oh, we use a lot of memory. For time, we first traverse through the create the tree and traverse through it. Actually, each node will be traversed exactly once, so it's linear time here. Yeah. Space, we use a 2 map, which for each map there will be a node connected to the other nodes, another cities. But actually, we are only n-1 roads, so there will be only one n-1 connections in these 2 maps. So it's 2n for the space, and for the here we use a recursion. So it has a call stack. The length worst case is n. So in total is still linear space. Well, for our submission actually is not that fast. So could we improve it? Well, it's linear time. There's what I can think of is that we could rewrite it into iteration. But I didn't change the space here. Well, could we change the space here? Could we change the space here? Maybe. We're checking the inbound and outbound. Maybe rather than create 2 maps, maybe we could use only 1 map, but keep track of the relation. Like we could use a map like a map city, but use a set. Or not set, we use another map, right? Use another map, and this one is a city, and the other one is inbound or outbound. With this good. So when we're traversing through, like we're getting 0, 1, we get a map 0 to 1 with inbound. And for 1, for 0, 1, for 0, it's outbound. For 1, it's inbound. For that, if that's the case, rather than we wait a minute, there's no outbound or inbound map. It's just the map, right? And when we're walking down the tree, well, actually we will do the same. Yeah, actually we'll do the same. We still need to look through all the connections and determine it is inbound or outbound, right? Yeah. Yeah. Okay. I'll stop here. Hope it helps. See you next time. Bye bye.